Welcome to this session on convolution property of Laplace transform. The convolution of two functions f of t and g of t is denoted by f of t star g of t. This is the notation for convolution, or we can write like this: f star g of t, and is defined as f of t star g of t, that is f of t convolution g of t, is equal to the integral from 0 to t f of u into g of t minus u du. This is the definition of convolution, that is convolution of two functions in t, f of t and g of t, is obtained by integrating this product. In f of t, just replace t by u, and in g of t, we replace t by t minus u, then taking the product of these two functions and then integrating with respect to u between the limits 0 and t, which is the definition of convolution. Now, the convolution property of Laplace transform is, if Laplace transform of a function f of t is equal to f of s, and Laplace transform of another function in t, that is L of g of t is equal to g of s, then the Laplace transform of f of t convolution g of t is equal to f of s into g of s. This is the convolution property of Laplace transform. That is, this can be written as f of s is Laplace transform of f of t into g of s is Laplace transform of g of t. That is, if we multiply the two Laplace transforms, that is, first one is Laplace transform of f of t and second one is the Laplace transform of g of t, then we will get the Laplace transform of this convolution f of t star g of t. Now, consider the inverse Laplace transform of this statement. We can write, if L inverse of f of s is equal to f of t and L inverse of g of s is equal to g of t, then we can write L inverse of f of s into g of s. From here we can write L inverse of f of s into g of s is equal to f of t star g of t. This is the inverse statement of this property. We can find the inverse Laplace transform of this product f of s and g of s by taking the convolution of the corresponding functions f of t and g of t. Your f of t is the inverse Laplace transform of f of s and g of t is the inverse Laplace transform of g of s. Now, consider this example. evaluate integral from 0 to t u into sin t minus u du. We have the convolution. Definition of convolution is f of t star g of t is equal to integral from 0 to t f of u into g of t minus u du. And we have the property, convolution property, L of f of t star g of t is equal to f of s into g of s, where f of s is the Laplace transform of f of t and g of s is the Laplace transform of g of t. Now, consider this integral. Comparing with the definition of this convolution, here instead of f of u it is u and g of t minus u it is sin t minus u. Therefore, we can write this as t convolution sin t. That is, the given integral is the convolution of t and sin t. Here t star sin t means consider this and taking inverse means f of t star g of t is equal to, we can write L inverse of f of s into g of s. Therefore, from here we can write this is equal to L inverse of, here f of s instead of from this we can write L inverse of f of s means Laplace transform of this t, that is 1 by s square, into g of s means Laplace transform of sin t, that is 1 by s square plus 1. That is equal to L inverse of 1 by s square into s square plus 1. Now, in order to find this inverse, we have L inverse of 1 by s square plus 1 is sin t. Then L inverse of 1 by s square plus 1 divided by s is, that is we have the property division by s in the inverse. Then corresponding change is, we can integrate this function, that is L inverse of 1 by s square plus 1, that is integral from 0 to t sin t dt, which is equal to integral of sin t is minus cos t between the limits 0 and t, that is equal to minus of cos t, when we apply the upper limit it is cos t, minus when t equal to 0 it is 1. Therefore, this is equal to 1 minus cos t, and L inverse of 1 by s square plus 1 divided by s, all divided by s, which is same as L inverse of 1 by s square into s square plus 1. We can write L inverse of 1 by s square into s square plus 1 as L inverse of 1 by s square plus 1 divided by s, all divided by s, and L inverse of this numerator function is 1 minus cos t. Therefore, if we divide this function by s, the corresponding change in the right hand side is, once again we have to integrate this inverse between the limits 0 and t, that is equal to integral from 0 to t 1 minus cos t dt, which is equal to t minus integral of cos t is sin t between the limits 0 and t, which is equal to t minus sin t, and when we apply the lower limit, this is for upper limit. If we apply the lower limit 0, the two terms will become 0. Therefore, t minus sin t, that is L inverse of 1 by s square into s square plus 1 is t minus sin t. Therefore, value of this integral is t minus sin t. This is equal to t minus sin t. Now, consider another example. Obtain the inverse Laplace transform of 1 by s square plus a square the whole square. We have to find the inverse Laplace transform of 1 by s square plus a square the whole square. Now, we can write this function as this is equal to L inverse of 1 by a square into a by s square plus a square into a by s square plus a square. This 1 by a square can be taken outside of this inverse Laplace transform. Therefore, this is equal to 1 by a square into L inverse of a by s square plus a square into a by a square plus a square. Now, consider the inverse Laplace transform of consider the inverse of convolution property. We can write from here, we can write L inverse of f of s into g of s, that is f of t star g of t. Here f of s is a by s square plus a square and g of s is a by s square plus a square, both are same. Therefore, we can write this as 1 by a square into f of t star g of t means L inverse of f of t is L inverse of f of s, convolution g of t is L inverse of g of s. Therefore, from here we can write this is equal to 1 by a square into L inverse of a by a square plus a square, convolution L inverse of a by a square plus a square. That is equal to 1 by a square into L inverse of a by a square plus a square is sin a t star, here also sin a t, that is sin a t convolution sin a t. By the definition of convolution, we can write this as this is equal to 1 by a square into, here this is the convolution. By the definition of convolution, it is integral from 0 to t sin au into sin a t minus u du. In one function we replace t by u, and in the other function we replace t by t minus u, and then taking the product and integrate between the limits 0 and t with respect to u, which is the definition of convolution. This is equal to 1 by a square into, here we can write integral from 0 to t. This is sin a sin b format. This is in the form 2 sin a sin b, not 2 sin a sin b. Therefore, we can write this as cos 1 by 2 into cos 2 au minus a t minus cos a t. du. This is equal to, this 1 by 2 can be taken outside of the integral. This is equal to 1 by 2 a square into integral from 0 to t cos 2 au minus a t minus cos a t du, which is equal to, here the integration is with respect to u. Therefore, this is equal to 1 by 2 a square into integral cos 2 au minus a t is sin a t sin 2 au minus a t divided by the coefficient of u is 2a minus, here cos a t is a constant, integration is with respect to u. Therefore, integral cos a t du is u into cos a t between the limits 0 and t. Which is equal to 1 by 2 a square into sin a t. When applying the upper limit for u, this will become sin 2 a t minus a t, that is sin a t by 2a minus, this will become t into cos a t, t into cos a t. When applying this lower limit 0 for u, this term will become sin 0 minus a t divided by 2a, that is sin minus a t divided by 2a. Sin minus theta is minus sin theta. Therefore, this will become plus sin a t divided by 2a. When u equal to 0, this term will become 0. This is equal to 1 by 2 a square into sin a t by 2a, sin a t by 2a plus sin a t by 2a is 2 times sin a t by 2a, that is sin a t by a minus t cos a t. This can be written as 1 by 2 a cube into sin a t minus a t cos a t. This is the required inverse of this given function 1 by a square plus a square the whole square. Now, consider another one example to find the inverse Laplace transform using the convolution property of Laplace transform. Evaluate L inverse of 1 by s plus 1 into s square minus 4. We have to evaluate this. This can be written as L inverse of, here we can write 1 by s plus 1 into 1 by s square minus 4. This is of the form L inverse of f of s into g of s, which is equal to L inverse of, by the property of inverse property of convolution, we can write this is as L inverse of 1 by s plus 1 star L inverse of 1 by s square minus 4, because the Laplace transform of this convolution f of t star g of t is f of s into g of s, means if we are taking the inverses, we can write this as L inverse of f of s into g of s is equal to f of t star g of t. But f of t star g of t means L inverse of f of s star g of t is L inverse of g of s. Therefore, this is equal to L inverse of 1 by s plus 1 is e raised to minus t convolution. L inverse of 1 by s square minus 4 is 1 by 2 into sin h 2t. We have L inverse of a by s square minus a square is equal to sin h a t. Here instead of a, it is 2, 4 means 2 square, therefore we can write this L inverse of 1 by s square minus 2 square. Instead of a, it is 2. Therefore, we can write L inverse of 1 by s square minus 4 is equal to 1 by 2 into sin h 2t, which is equal to 1 by 2 into e raised to minus t convolution sin h 2t. 1 by 2 is a constant. Constant can taken outside of the convolution. We can write this e of minus t convolution sin h 2t. By the definition of convolution, this is equal to 1 by 2 into integral from 0 to t e raised to minus of t minus u into sin h 2t. Sorry, here sin h 2u. We replace t by u, and in this first taking f of t as sin h 2t and g of t as e raised to minus t. In f of t, we replace t by u, and in the second function g of t, we replace t by t minus u, and then taking the product, then integrate with respect to u between the limits 0 and t, which is the definition of convolution. This is equal to, we can write 1 by 2 into integral from 0 to t. Here e raised to minus t into e raised to u. In the exponent, it is minus t plus u, which can be written as e raised to minus t into e raised to u sin h 2u du. That is e raised to 2u minus e raised to minus 2u divided by 2 du, because sin h theta is e raised to theta minus e raised to minus theta all divided by 2. Therefore, we write sin h 2u as e raised to 2u minus e raised to minus 2u divided by 2. which is equal to this 1 by 2 into 1 by 2 is 1 by 4. Here integration is with respect to u. Therefore, this term e raised to minus t can be taken outside of the integral into integral from 0 to t. Here e raised to u into e raised to 2u. E raised to u into e raised to 2u means e raised to u plus 2u is 3u minus e raised to u into e raised to minus 2u means e raised to u minus 2u, that is e raised to minus u du. On integration, we get this equal to 1 by 4 into e raised to minus t into e raised to 3u du means e raised to 3u divided by 3 minus integral of this e raised to minus u is e raised to minus u divided by minus 1 between the limits 0 and t. This is equal to 1 by 4 into e raised to minus t. When we apply the upper limit, this will become here minus of minus means we can write this as plus e raised to minus u. When we apply the upper limit t, we get e raised to 3t by 3 plus e raised to minus t. When we apply the lower limit 0, this term will become e raised to 0. In the numerator, this term will become e raised to 0, that is 1. That means 1 by 3, minus 1 by 3, because the lower limit minus this 1. That is equal to 1 by 4 into e raised to minus t into here e raised to 3t by 3 plus e raised to minus t. Here minus 1 by 3 minus 1 means minus 4 by 3. This is the required inverse of this function. With this example, I would like to conclude this session. Thank you for listening the class. Have a nice day.